Hello my dear students, so welcome to my YouTube channel. So this video is about the numericals of the solution chapter. So in the previous video, if you have gone through, I discussed about the numericals and how to solve and how to remember the formula. And from 2014 to till 2020, we solved solid state numericals and including the model question paper. And as I told, I have given the PDF file of this one even in my Telegram channel. I have mentioned the link as well. Okay, even in this video, okay, we will discuss the numericals of a solution chapter. Okay, and I'll going to give the PDF file of this one in my Telegram channel. You can go through that one. So in this video, what I'll going to do, I'll going to discuss about the formulae first. Okay, so which are all the formula that you had to remember and how to remember the terms, how to remember. These all things I'll going to discuss today. Okay, and in my next video, I'll going to do numericals of 2014 to 20 as well as about the model question paper. So here you could see the main thing that you had to remember while solving the solution chapter question. The first point is that in your question paper, 28th question, that to 28th A, okay, will be from the solution chapter. So there is a condition that the numerical that is asked for the question number 28A should be on a colligative property. Okay, so as we all know, there are 4 colligative property according to a syllabus. Okay, so those 4 colligative property formula you have to remember, dear students. Okay, so that is relative lowering of a vapor pressure, okay, and elevation in boiling point, depression in freezing point, as well as the osmotic pressure. So all this formula you have to remember. Now, and one more point you have to remember that, so whatever the formula I have written over here, you could see I have mentioned A and in B, okay, and here also you could see A, B, like that. So you should know what is A, what is B, then only you can solve the numericals. So here A represents solvent, pure solvent, B represent solute. Where in some cases, in some colleges, they have taught in this way, 1 equal to as a solvent, okay, where 2 is equal to as a solute, like W1, W2, like that also they have mentioned. But here I am taking A as a solvent and B as a solute. This one point you have to remember compulsory before going to solve any numerical. Okay, so now you could see here, so the first colligative property I have taken over here, relative lowering of a vapor pressure. Okay, so delta P is equal to, that is the difference in a vapor pressure, that is the vapor pressure of a pure solvent. So whenever you're going to see A, it's a solvent, that's a pure solvent, you had to remember. And not represents, here you have a not, dear students, that not represents what? It is pure solvent, it's in a pure condition. So remember, not represents, it's in a pure condition. So delta P is equal to P naught A minus PA, that is vapor pressure of a pure solvent minus vapor pressure of a solute we can consider. Okay, so now PA is equal to P naught A. See here, A I have told you about, it's a solvent. So it's a pure, and here it may be a solution. Means it may consist of some amount of a solute in this one. So that's why P naught A minus PA. Okay. Now, what is PA? This is another relation you have to remember. PA is equal to, that is vapor pressure of a solution is equal to, it's a product of vapor pressure of a pure solvent into 1 minus mole fraction of a solute, that is XA plus XB. That mole fraction of a solvent and the solute is always equal to 1. So this all formula you have to remember. How are you going to remember? You have to write it, you have to practice it. Okay, now this is very important, dear students. So here MB is equal to WB into MA into P naught A divided by WA into P naught A minus P. Okay, what is MB? It is, here I have written what all those terms means. Okay, MB, B means I told it's a solute. Capital M represents molar mass of the solute. WB represents weight of the solute or mass of the solute. MA represents molar mass of the solvent. P0A represents vapor pressure of a pure solvent. WA represents the weight of a pure solvent. And P0A minus PA is nothing but of delta P that I have already told. Okay, so this formula you have to remember. So dear students, further I'll going to tell. Okay, now the second formula is elevation in boiling point represented by delta TB. So delta TB is equal to TB minus T naught B. TB represents what? The boiling point. Okay. So elevation in boiling point is the difference between the boiling point of a solution minus the boiling point of a pure. Not represents pure. Okay, so delta TB is equal to TB minus T naught B. This is the difference in boiling point of a solution and the pure solvent. That is nothing but elevation in boiling point. So this one also had to remember delta TB is equal to KB into M. KB is ebullioscopic constant. Usually in your numerical they are going to give this value. And M represents molality. Okay, now this is a relationship between molar mass of the solute and the elevation in boiling point. MB is equal to KB into WB into 1000 divided by delta TB into WA. In some cases, they are going to give you the elevation in boiling point directly, or in some numericals, they are going to give both these values and you have to subtract and you have to find out the delta TB. Okay, so that while solving the numericals, I will going to explain. So MB means what? Molar mass of the solute. KB means what? Ebullioscopic constant. I have mentioned over here. You can go through later. WB means weight of the solute. Delta TB is elevation in boiling point. WA means weight of a solvent. Next one. So remembering these two formula is very easy, dear students. Okay, why? I'll explain this. Depression in freezing point represented by delta TF. So delta TF is equal to T naught F minus TF. So here we went through TB minus T naught B, but here T naught F minus TF. What do you mean by TF? Freezing temperature or freezing point of a pure solvent minus freezing point of a solution. Okay, T naught F minus TF. So now MB is equal to molar mass of a solute. If you want to find out, that's equal to KF into WB into 1000 divided by delta TF into WA. So KF, KB, WB, 1000, delta TF, WA, delta TB, WA. Only these two terms are changing over here. So if you remember this formula, and you can write this formula very easily, only thing you have to change KB as a KF, delta TB as a delta TF. Okay, so WB is weight of the solute, WA is weight of the pure solvent, MB is molar mass of the solute. And the last one that you have to remember is osmotic pressure. Okay, osmotic pressure is represented by pi. So here it's a relationship between the molar mass of the solute and the osmotic pressure. So MB is equal to WB into RT divided by pi into V. WB is weight of the solute, R is universal gas constant, I have mentioned its value also, and T is temperature, pi is osmotic pressure, V is volume of the solvent or the solution. Okay, they're going to give it. So these are the four formula you have to remember compulsory. So in all the four formula you can observe here, molar mass of the solute and the colligative property are inversely proportional. Okay, you could see molar mass of the solute and the relative lowering of vapor pressure inversely proportional. Molar mass of the solute, elevation in boiling point, inversely proportional. And here molar mass of the solute and depression in freezing point, both are inversely proportional. And here in case of osmotic pressure, molar mass of the solute and the osmotic pressure are inversely proportional. So one point you can keep in your mind that both are inversely. If molar mass of the solute you are writing here, obviously the colligative property will come to the denominator. Okay, so do practice and write. the formula. So in the next video, what are all the terms also I have mentioned here. Okay, so in the next video we will going to solve the numericals from 2020 to 20 to 2014 as well as a model question paper. Okay, so just wait for my next video. We're going to discuss about the numerical. Thank you.